afternoon, everyone. It gives me great honor and pleasure to welcome Dr. James Abdey, Assistant Professorial Lecturer at the London School of Economics and Political Science. Dr. Abdey holds a bachelor's and a master's degree in economics and statistics from the University of Exeter, a doctorate in stats from the London School of Economics. He has also been a visiting lecturer at the Kazakh British Technical University and the Singapore Institute of Management. His major areas of lecturing are in elementary statistical theory, quantitative methods, aspect of market research and market research methods. On behalf of the ISBF student fraternity, I extend a warm welcome to you, sir. May I also request our director, Nikita to present a bouquet of flowers.
Oh, thank you very much. Wow, thank you. Namaste. That's all I know. Hello everybody, welcome, hello, hi. This is my first time in India. I've been in India all of about 3 hours so far. So, and I've been drugged up with caffeine, so there's no jet lag at the moment. So a very warm welcome to this session. I'm delighted to be here. As you may be aware, because I guess you are doing Statistics 1, I am the subject guide author for Statistics 1, so you can now put a face to the name. I've been asked to run various sessions here today and tomorrow. I'll be exploring a little bit more of India. I'll be heading down to Mumbai and then down to Sri Lanka before going back to London. But I was asked in this first session to say a little bit about interval estimation and also to explain the sort of rationale behind why you're studying quantitative courses as part of the EMF SS programs. Now, I was quite interested there to hear about my life story, my biography. If I may, I'd just like to perhaps pick up on that. So you've heard some details about me, and that's all true. It's all true. So if I may, I'd like to begin with a question to you all. Okay, I'd like to see if you can come up with an answer to this question. How old am I? Any estimates? Any estimates for my age?
37.
30. I have 37. Okay, 37. Does anyone think I'm older than 37? Yeah. Okay. How old?
43.
Okay. 45. Anyone think I'm older than 45? Okay, so we have 45 as like an upper bound there. Now let's go down below the 37. Anyone thinks I'm younger than 37? 33. Anyone think I'm younger than 33?
30.
30. Are we all done at 30? Any bits lower than 30? Okay, we're done. The auction is over there. So we now have an interval estimate for my age, running from 30, sorry, what was it, to 45. That's a 15-year interval range. But an example there of an interval estimate. Now, I know my age. I have my passport right here. I can prove what my age is. Now, I know the truth. You do not. So, I asked you to come up initially with some point estimates. And we had 37, 45, 33, 30, etc. And now we've concluded with an interval estimate. So, am I right in thinking everyone in this room thinks I am between 30 and 45? Is that fair to say? Okay. So, could we say that you are 100% confident? I see the link, this is clever. That you are 100% confident I'm between 30 and 45. Excellent. Now, that is quite a wide interval. Let's try and narrow this interval slightly. So, I heard, I think, like 33 and 37 say. Now, clearly not everyone in this room thinks I am between 33 and 37. Well, I would guess the majority of you do. Let's just keep the numbers simple. Let's assume we are perhaps, or you are 95% confident I am between 33 and 37. Now, which one of those is the better interval? The first one or the second one? 30 to 45 or 33 to 37? Let's put it to the vote. Hands up if you think the 30 to 45 interval is the better one. Hello, hi. Okay. Hands up if you think the 33 to 37 one is the better interval. Okay. Ooh. I'm going to give you a third option. Oh, I'm being photoed. Let's have a third option. Hands up for, well, James, it depends. You may vote again. Excellent. If you learn nothing else from this talk, please take away that the answer to all of life's questions is, it depends. It's clearly a trade-off. We have two intervals. There is a cost and a benefit. Advantages and disadvantages. Always think in those terms. If you're studying economics, things like opportunity costs. E.g., you can be here now listening to me, or you could be outside or having lunch or doing something else. You can do both of those things at the same time. So let's consider those two intervals. The 30 to 45. The advantage is everyone in this room thought I was between those ages. We had 100% confidence. Other things equal, that's good. But we have a very wide interval. Now let's consider the second one. It is a shorter interval, 33 to 37, only 4 years, say. Greater precision, which is a good thing, but not all of you were convinced that I was between that range of values, so a bad thing. So costs and benefits, and which is better? Well, it depends. Well, I'll share with you my true age. I am, of course, 47. There we go. I was just curious about the facial expressions of some of you. Who am I? So, I'm. But an example there of estimation. Tell me, how did you come up with those initial estimates of like 37, 33, or etc.? On what basis did you come up with those values?
Looks.
Looks! Okay, oh, dare I ask, describe my looks. Oh, no comment. Okay. Looks, good. Anything else at the back? Yeah. Ah! Okay. So you basically collected data. Maybe quantitative, maybe qualitative. Looks. It's not quantitative. You're getting some, just looking at my visual, the look of my face. Data in terms of perhaps my educational background. Now, clearly you know some pieces of information about me. You can all look at me and judge my age based on my looks. You can indeed judge my approximate age, perhaps based on my academic record. If I've got a bachelor's degree, a master's, a PhD, etc., clearly that takes some time to pursue, and clearly I'm unlikely to be about 18 or 20, say. So based on some incomplete information, you can start to build a view of things. You can start to estimate things. Now indeed, that 30 to 45 range, I mean the 33 to 37 range, is actually pretty good indeed, and you form that based on observations. Okay, think of the data you've obtained, my looks, my educational background, say. Think of this as a sample, okay, drawn from the population of data about me. Now, clearly you know some things about me. There are many things about me you don't know. We all have secrets. But that's really what we do with estimation in statistics. We will collect data, okay, maybe not the looks of someone, maybe not their CV necessarily. We're thinking about collecting a sample drawn from a wider population. That's our data, and from that we're going to try and estimate some parameter of interest. So clearly there's uncertainty. You still don't know my exact age, but you can come up with a reasonable guess. So, oh, hello. Oh, there we go. Interval estimation. Good news, I will arrange for these lovely slides to be circulated among you later on, so you don't need to worry about taking any notes now. But I'll just go through a few examples from Statistics 1 about interval estimation. Some may be exam-style questions, others not, but it's hopefully will give you a good understanding about what interval estimation involves. Actually, before we start looking at any of those slides, I've got some really good news for you. Where is it? Okay. In your Stats 1 exam, you get a formula sheet. Who do you have to thank for having a formula sheet? Your predecessors many years ago did not have a formula sheet. Many years ago, there was no formula sheet in Stats 1, and students had to memorise all of these formulae. So, having a formula sheet, is it a good thing or a bad thing? Hands up for it's a good thing. Wow, consensus. Hands up for it's a bad thing. Some dissent in the room. Hands up for, well, James, it depends. Of course, it depends. It seems an advantage. And other things equal, clearly having a formula sheet is better than not having a formula sheet. In economics, at various levels, it's often talked about other things being equal. Ceteris paribus from Latin. Well, that's all very well in a dry academic setting, but in the real world, other things are not equal. When you change something, other things change as well. Those are two confidence intervals we came up with. We had a wide one, 30 to 45. We reduced it to 33 to 37. So other things were not equal. Two things changed. Yes, we had a shorter interval indicating greater precision. Good. But we had a lower level of confidence, which was bad. Other things equal. Clearly having this thing is good, but clearly other things are not equal. Yes, this is a benefit. Think about costs and benefits. Whenever there's a benefit, there's always a cost. What really matters is, does the benefit at least offset the cost? Now, I would argue, on balance, yes, having that formula sheet is a good thing. But just to briefly think about what the cost is. So in the days before the formula sheet, in the exam, students would get marks just for remembering the appropriate formula and writing it down. Well, clearly it will be far too generous of us to award you marks for just literally copying something down off a formula sheet. So clearly those marks no longer apply and are no longer able to be obtained. That is the cost. However, given the amount of time it's going to save you from having to memorise all of these, I would say, in next terms, indeed, this is quite a considerable benefit to you. Intervals, but as and when you get to it, the hypothesis testing too. Now, what we're going to have a quick look through this afternoon is just a few examples extracted from this formula sheet, applied in a few settings. So in the exam, the lovely thing you'll be doing in May next year, highly likely that there will be some confidence interval question or questions within there. So we'll look at some of the key ingredients for what might make a good confidence interval answer. So the introduction of the formula sheet. So marks have now been taken away. You don't get marks for writing out the formulae, which suggests you will get marks somehow else. So more marks are now awarded to the interpretation of results. You've got a formula, you've got your calculator, you can tap in the numbers and calculate your interval. And there will be some credit for that, but more emphasis now in Stats 1 on interpreting the results. What do these mean in the context of the problem? So, again, you'll get all of these slides, and I encourage you to have a review of these at your leisure. So first of all, just some general words of advice. Now this is not specific to interval estimation. Indeed, it's not specific to Statistics 1. This is applicable to any quantitative course that you study this year and in the years ahead. We like you to get the right answers in any question, of course. However, the majority of marks are awarded for the method. Now, the answer in, say, stats is a number, or a range of numbers for an interval. I personally do not care that much what numerical values they are. I do care about how you get to those values. Now, calculating that final answer means, can you use a calculator? Well, that's nothing too dramatic to show an examiner. But really, it's the method which counts. So please, I implore you to always show your method and explain your method. Explain can mean writing some words. Now, I'm a statistician, which means I hate essays, which means when I say write words, you are not writing a huge essay in support of your answer. I do mean 2 or 3 words, a short sentence at most, to explain what's going on. Because the whole point of the examination is for you to signal to the examiners that you know what you are doing. And indeed, that word signal explains why you are here right now pursuing your degree. An education is a signal. You know you're brilliant. I know you're brilliant. But does the outside world know you're brilliant? No, they don't. So how do you distinguish yourselves from less brilliant people? Well, you need some signal to distinguish between one group and another group. And that signal is coming from your education. It is difficult to pursue a degree. So clearly you want to be rewarded for that effort. And by holding that piece of paper up, that degree certificate at the end of it, this is a signal to the wider world of your abilities, and hence good for your careers. You can get every answer wrong in the Stats 1 exam and still get a first-class mark. No. Yes. Because maybe you've used exactly the correct method in every single question, but you made silly calculation errors. You pressed plus instead of minus on your calculator, say. Maybe all of your numerical results are wrong. But those mistakes are due to perhaps very small things like a miscalculation. But provided the approach that's been adopted is correct, you will qualify for a vast majority of the marks. So I'm not going to go through these in complete detail. You are going to get these slides later on, but I will just highlight some key points. So you have your formula sheet, and clearly there are different sorts of things we wish to estimate. Now, as far as statistics 1 is concerned, we'll tend to focus on 4 types of interval. We're either estimating a mean, we're estimating a proportion, or we are comparing two means, the difference between them, or perhaps comparing and looking at the difference between two proportions. That's basically it. You have the corresponding confidence interval formulae on the formula sheet. So arguably the most challenging part of any confidence interval question is to decide, what are you trying to estimate? Is it a mean? Is it a proportion? Is it two means or two proportions? Once you've established that, one can just really go to your formula sheet, extract the corresponding formula, use your statistical tables, and we'll quickly see those in a moment, and work out your interval and then interpret it. So first of all, the distinction between a single mean or a single proportion, let's say on this side, and comparing two means or two proportions on this side. Well, if I'm only comparing, I'm sorry, I'm going backwards and forwards, you're having to move around a lot with the camera, apologies. If it's just a single mean or a single proportion, that means you will have one sample available to you, one random sample. If you're comparing two means, two proportions, you will have data within the question relating to two samples. I spy with my little eye only one sample here, so this is either a single mean or a single proportion. I've got a keyword there in the question of a mean reaction time. Indeed, we're looking at the reaction times in seconds of 8 police officers. So the estimation there of a mean. One can jump to our formula sheet. I won't keep cross-referencing that between the documents, but our confidence interval formula for estimating a mean when the variance of the population is unknown. Now, before we get into perhaps the details of the equation, just think in basic terms. I'm coming forward now, I'm sorry. So we use interval estimation for the following purposes. First of all, I heard like 37 was mentioned when I asked for my age. That was a single value, a point estimate. That was your best guess of my age based on the information you had. Clearly you weren't certain I was 37. I could be 37, but you're not entirely sure of that fact. So what you really want to do is to convert your point estimate, that best guess, into an interval estimate, a range of plausible values, which you think, in that case, my age could be. So when we take our point estimate, our simple sample mean there, we want to attach to it a margin of error, a margin of error. Now, remember very early on in Stats 1, data presentation, descriptive statistics, sample means, sample variances, sample standard deviations, simple descriptive or summary statistics to summarize certain key aspects of a sample distribution. Remember your sample mean, that measure of a central tendency, or on average, what was the typical reaction time, in this case we observed in our sample. S, sample standard deviation, a measure of the variation we see in our sample. And indeed, just eyeballing the reaction times recorded, they are not all the same value. There is some variation within these values. Indeed, there's variation in all sorts of things. Perhaps take another variable, height. We all have a height in this room. Different heights. There will be some tall people in this room, there will be some short people in this room. There will be an average height of people in this room, but there will be some quite considerable variation, I'm guessing, within that. Actually, very quickly, could I just have, perhaps at the front, could I quickly have 10 volunteers at the front? Perhaps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll join in this exercise. Nothing bad, you just got to stand at the front. Okay. Just like to show you one thing. Please stand up and face your peers. Okay, I would now like us to arrange ourselves in height order. Let's have shortest over there to tallest over there. I'll participate in this as well. So shortest on this side, tallest over there. Okay. There we go. There we go. Okay. And the rest of the room decide whether we are approximately right in this. And where do I go? Here? Okay. Okay. So I do perhaps a panoramic shot here. So visually now you can start to see what we mean by variation. Height is the variable. Of this sample of people that we have here, there is an average height. We're not going to measure our individual heights. Interesting indeed. So we are now arranged in height, and there is variation in our heights. What's causing this variation? I don't know. Maybe our genetics, maybe what food we eat, whatever. Any interesting features you note about us standing up here? Would you agree that those of us in the middle here, we're not exactly the same height, but we are quite similar heights, okay? Whereas the outliers, and I mean that in a nice way, I really do. Well, our outliers there are more extreme, but as a proportion of the sample, quite minimal. Now, keep in your mind now a normal distribution. Remember studying that? Okay, yeah. So we might think that height is approximately normally distributed. You are not seeing a bell-shaped curve in front of you because we're going from shortest to tallest, and it's going up like that. But remember, a normal distribution, that bell-shaped curve. So we're looking at a large proportion, in this case of our sample, in the middle, where the variation in heights is quite minimal, and then in the tail ends, 1 or 2 individuals at most perhaps, who are in the tails of that distribution. So we can see, for example, height following approximately a normal distribution. Admittedly, our sample size here, our n, is quite small, and are we a representative sample? Are we a representative sample? Hands up, yes. Hands up, no. Hands up, well, James, it depends. Well, if we're thinking about height, I don't think necessarily why we might be an unrepresentative sample, unless shorter people tend to sit at the front so they can see more and the tall people stand at the back, but I don't think that's necessarily been the case here today. So as far as height is concerned, I think we could be classified as a representative sample. If we're looking at other characteristics, e.g. our educational levels, clearly we are not representative of a general population. Most people in the world will not pursue higher education. So you are in the sort of the top few percentile of the global population as far as your education is concerned. Can we just have a quick round of applause, please? So remember, S there. We could have collected the heights, measured the height of those people, and the sample standard deviation, a measure of the variation there. So turning this now back to our confidence interval. So there is a sample. I could have done this with heights instead of reaction times. Calculate a sample mean, calculate a sample standard deviation. Basic stuff early on in the subject guide. I'd like us just to focus on this margin of error for estimating a mean. We can plug numbers into a calculator. Getting this final answer is not that difficult. but I'd like you to have a good understanding about the ingredients of this margin of error, which clearly have an impact on how wide this interval is. And we can see that there are three ingredients there. In no particular order, let's take that n. We see the square root of n there in the denominator. Other things equal, and I do wish to use that phrase here, as n goes up, this margin of error is going to go down. So we're now dividing by a larger number. And is this as we might expect? I would argue, yes. Other things equal, better to have a large sample size than a small sample size. We'll have greater precision in our estimates. Now, we could have done the heights of those 9, 10 of us standing here. Would have been better to have perhaps the heights of everyone within this room. So, other things equal, as n goes up, we'll have greater precision, and this will tend to reduce the width of our confidence interval. Okay. Of course, though, there is a trade-off. As n goes up, we get more precise intervals. That's a good thing, that's a benefit. But remember, there's always a cost. The cost here, of course, is time and money. The data collection costs. It takes longer to collect data on a larger number of observations. So appreciate the impact of n on the width of the confidence interval. S, the measure of variation. Of course, this would act as an estimate of the population standard deviation, sigma. Because throughout all of this statistical inference, there's an underlying assumption that our random sample is representative of the population. We can't know for sure whether we have a representative sample. We hope we do. And hence the characteristics of the sample should be approximately equal to the corresponding characteristics in the population. So, for example, x bar, the sample mean, should be approximately equal to mu, the population mean. Just as S, the sample standard deviation, should be approximately equal to the true population standard deviation. But there's always a risk, by chance, if we have an unrepresentative sample, say. So now let's think about the impact of S on the confidence interval width. As S goes up, meaning there's greater variation within our sample, which is indicative of greater variation within the population. Well, the more varied the population, the harder it is to ensure a fairly representative sample is obtained. And hence, the greater the variation which exists, here, as S gets bigger, other things equal, the margin of error gets larger and the interval becomes wider. If S was very small, that means there's very little variation, let's say in the heights of people or the reaction times. They're very, very similar. Then we would expect quite a great precision in our estimate of the mean and a very short interval. S is nothing we can actually do anything about. S will be driven by what the true sigma is. Whether this is big or small, we'd like it to be small, but we have no control over this. We can do nothing about it. If it's a very diverse population, then it's a diverse population. N is under my control. I can decide my sample size, 10, 20, 50, 100, 1,000 or more. Then we have our third component here, this confidence coefficient. So this too is going to have an impact on the final interval calculated. So again, there are trade-offs. We sort of briefly mentioned this with the age example earlier. 100% confidence, 95% confidence, etc. So is there... is this okay to use on the board? Okay. Just to take a very recent example. On November the 8th, there was a presidential election in the US. I'm sure you've heard about that in the news. Okay. We were discussing this briefly over lunch. And there are many opinion polls taken in the run-up to that election, which consistently gave Hillary Clinton about a 3 to 4 percentage point lead over Trump. It fluctuated a little bit. But let's just consider a very simple example of a confidence interval in the US presidential election. In opinion polling, sample sizes tend to be about 1,000. Reasons we'll, if time permitting, we will get back onto, but that's the industry standard. So in this case, we are estimating a proportion. I like to know the proportion of the electorate who would support Hillary Clinton and vote for Hillary Clinton, or Donald Trump. We could do it either way. So let's look at the Clinton one as an example. So, of course, this true value is unknown. It's only known on polling day, when people go to the voting booths, cast their vote by paper or electronically, the votes are counted and we know the end result. Now, clearly, ahead of the election, we'd like to estimate what this value is. So we take 1,000 people and we say, will you vote for Clinton in the forthcoming election? Let's say 450 said, yes, I will. So now we can come up with a simple point estimate. R over N, the 450 over 1,000, giving us a sample proportion of 0.45, or as a percentage, 45%. So typically when the opinion polls are reported in the media, I'm no artist, but what you tend to see is a sort of face. Again, I'm no artist, but there you go. A face of the candidate, their picture, and then a percentage attached next to it to indicate what the opinion poll is predicting. If you ever read the small print of opinion polls, it will then discuss the margin of error which is attached to opinion polls. And given sample sizes of 1,000, given the industry acceptance of having a 95% level of confidence, typically this leads to margins of error of the order of about 3 percentage points. So, point estimate, 45%, we can quickly convert it into an interval estimate. So I am 95% confident that Clinton would poll between 42% and 48% in this election. Let's, just for the sake of political balance, let's consider Trump as well. Let's suppose, again in this sample of 1,000 voters, let's say 430 said that they would vote for Trump, giving us our sample proportion there of 0.43 or 43%. Okay. So we can see this particular opinion poll is giving Clinton a lead of 2 percentage points. But there's also a margin of error here, still, of about 3 percentage points. So we can come up again with a 95% confidence interval, let's say between 40% and 46%. Notice here how these confidence intervals are overlapping. So although Clinton did have a sort of a historic poll lead, it was within the margin of error. So if I was Clinton, I would not be that, I shouldn't feel that confident going into the election. Now, of course, all of this is assuming representative samples. I'm digressing slightly from that confidence interval example, but highly relevant for Stats 1. Sampling design, so when you look at that, we like to have a representative sample. Well, maybe these are random samples, free of selection bias, but are they representative? So imagine this is our population, the US electorate. And from this, let's say a simple random sample of a size 1,000 is taken from it. We hope it's fairly representative. As we now know, all of these opinion polls got it wrong. Or did they? I mean, Trump did win the election, but Hillary Clinton did win the popular vote. Last figures I heard, she got roughly 2 million more votes than Donald Trump. So on a national basis, she actually did poll better than Trump. But this electoral college system they have meant that Trump ended up being the victor. However, just to consider and beware the potential for unrepresentative samples. There's been a big investigation by the polling companies about what went wrong. Why did no one really, or very few people, predict a Trump victory? Now, this is still under investigation, but I think it's perhaps a misdefined population. Are we considering the US electorate? Well, some people have the right to vote, but tend not to vote. And in the US, many voters have never bothered voting in elections before. So out of the total US electorate, maybe only this amount in previous elections had actively participated in elections. And the polling organisations made an assumption. Gosh, assumptions. Wow, we'll perhaps say a bit more on that a little bit later too. The perils of making assumptions. They assumed that people who didn't bother voting in previous elections would still stay at home this time round. Well, it seems, and hence, when they were drawing a sample, they were only focusing on this population. In truth, many of these people actually did bother voting this time round, and they tended to vote for Trump. So it's quite an easy explanation about why polling is still a good idea to do, but you do need a carefully defined population. Bias, something you will also touch on. There may be response bias here. Now, you may intend to vote for Trump in an election if it's not seen as a socially acceptable answer to give face-to-face with a pollster, then there may be response bias here. Some people said they would vote for Clinton when in the privacy of the voting booth they decide to vote for the other candidate. So some issues of sampling design we actually see coming into play in real life. So just to go back now to our confidence interval itself. So what level of confidence do we want? Well, just to perhaps go back to Clinton's one here, the 42 to 48%. I'm sure she, and no doubt Trump, had many statistical advisors to look at the polling figures. Suppose I fancied being Clinton's, or indeed Trump's, statistical advisor, and I get a job interview before the election took place. And my pitch for the job is as follows. Your current statistical advisor can give you only 95% confidence. I, though, can give you 100% confidence, Mr. Trump or Mrs. Clinton. And they go, wow, that's great, tell me more. I said, okay, I will give you a 100% confidence interval, which is better than just the only 95% your current guys and girls can give you. So, Mr. Trump, Mrs. Clinton, I am 100% confident that your level of support in the electorate is between this. I am certain. This is uncertain. I'm certain. Now you laugh, and quite rightly so. Why? Because we end up with an interval, and indeed I can be certain that Trump's or Clinton's support was between these values. However, this is of no practical use whatsoever. This is clearly far more informative to a candidate than saying it's somewhere between nothing and everything. Just as if I was estimating a mean. I could say I'm 100% confident a mean is between minus infinity and plus infinity, i.e. a real number. Great, but again of no practical use. So again, thinking about trade-offs. I am prepared to sacrifice a little bit of confidence, which is a bad thing, it's a cost, but I'm going to get a dramatic benefit by having a shorter confidence interval. However, when you do resolve trade-offs, typically there's no definitive right or wrong thing to do, but I do want you to appreciate what the trade-offs involve. And I want you thinking about things in terms of costs and benefits. Now, different people can propose different resolutions to a trade-off, and that's absolutely fine. It's an opinion-based thing at the end of the day. The important thing, though, is that you can defend and justify your particular position. So, just briefly on this confidence coefficient. Now again, you'll get these worked examples to have a look through yourselves, but if I may just draw your attention to the statistical tables. These statistical tables. Great things these are. I get many emails from students. This is a true story. Once upon a time, the day before an exam, not Stats 1, one of my internal exams at LSE, the night before the exam, I got an email from a student. I love it when I get emails from students, because students never quite know how to address the email to a lecturer, professor. You get various things. Some say, dear Mr. Abdey, dear Dr. Abdey, dear Professor Abdey, I get promoted, dear Sir James, I love that. Sometimes they are unsure which is the appropriate title, so they just write, hey! Once, I had an email from a student who said, dear Mrs. Abdey. Now, Now, when I received this, first of all, I thought, oh, perhaps, it was a student, maybe English wasn't their first language, it was a lost in translation thing. But this student, I could see that it was a native English speaker. So I thought, how do I respond to this email? Well, I need to do it in a clever way. I like to be clever. So I replied to the email, dear so-and-so, blah, 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 blah. Best wishes, James. P.S. And then said, I'm not married. So it can't be Mrs. Ms, maybe. I am now married, so sort of before those sometimes. Anyway, the night before an exam, I got an email that said, dear James, I've memorised the standard normal table and the T table, but I haven't had time. This is true. I haven't had time to memorise the chi-squared table in the exam. Will I be okay? Now, I hope it was a joke. However, there was just something about the tone of the email. It just had it just seemed a genuine email. And I just didn't quite know how to tell this student, I don't want to break their heart, that they must have spent days studiously running through those tables to memorise all of these values. You get the tables in the exam. The tables are not loading on here. Oh no. Let's try it. The tables are not loading. Let's try it. Okay. Oh. Try one more. Okay, well, we can do it without this. I'll just tell you the shortcut. With confidence interval questions, and for most hypothesis test questions as well, in fact, the key table to use will be table 10 for the T distribution. Okay, so we don't really need to see the actual table projected up. You just need to know about particular columns, and let's just do the hard work now. In an exam, it is highly likely, I won't say definitely, because there's always some uncertainty in life, of course, but highly likely that a confidence interval question would either be asking for 90% confidence, 95% confidence, let's say 98% confidence, and let's say maybe 99% confidence. It might be something else, but highly unlikely. Now maybe it's for a mean, maybe it's for a proportion. You've got the formula sheet, and it's either going to be some t value or a z value. So what will table 10 look like? On the far left-hand side, you're going to have some degrees of freedom. 1, 2, 3, 4, 5, dot, 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 and it goes down to infinity. Remembering that a t distribution with infinite degrees of freedom is in fact that standard normal distribution. So when you see infinity, just think z. So if on your formula sheet, as in doing confidence interval for, let's say, a proportion, there's a z appearing there, then you're going to be using that bottom line. So you can use the standard normal tables, but you can have everything in one place with table 10 with that t distribution. So, if it's z, you're going to the bottom row. If it's t with some degrees of freedom, the appropriate row here. Then in table 10, you have different columns of values. These talk about percentage points of the t distribution. Let's just perhaps do a quick sketch of the t distribution. Metric about 0. Total area under this curve is 1. This t distribution, this tail goes off down to minus infinity. It's a long way down there. This one goes all the way off to plus infinity. It's a long way over there. If I had a 100% confidence interval, and I was dealing with the t distribution, say, then my confidence coefficient would in fact be infinity. And this would give rise to an interval, an infinite width confidence interval. That would be to say, I think a true mean, mu, is a member of the real line, i.e. between minus infinity and plus infinity. Well, as we said, this is of no practical use. Just as the 0%, 100% for a proportion. No practical use. But why is this a 100% confidence interval? Well, it's making use of infinity as our confidence coefficient, where we are looking at 100% of the area under that curve. So we're going to undertake a trade-off. We will consider reducing that level of confidence a little bit. Let's say from 100%, let's go down to 99% first of all. This will go down this way. So what does that really mean in sort of visual terms? We are then interested in the central 99% probability of that distribution. Now, the good news is this distribution is symmetric, about 0, and if I'm looking at the central 99%, then the remaining 1% must be contained in those tail areas. But clearly, that's going to be split equally between those two tails. So if there's 100% overall under the curve, and I've got 99% here, then I'm going to have 0.5% in this lower tail, and of course 0.5% in this upper tail. And hence, when you go to table 10, because table 10 gives things in percentage points of the t distribution. So when you have that row of figures at the top of table 10, these are not probabilities, they are percentage points. Okay. So when you see, if for example you see 0.05, that's not 5%. That's in percentage point terms. So if you wanted a 99% confidence interval, then the appropriate column to look at in this table is going to be the one headed 0.5 for the 0.5 percentage points. So you then know the appropriate row, you know the appropriate column, get the intersection, and there is your value. Let's just go down. If I wanted the central 98%, the remaining 2% is split between these two tails, 1% here, 1% here. So in table 10, you want 1 percentage point in that upper tail. So it doesn't matter whether it's a mean or a proportion, 2 means 2 proportions, 98%, that's the column to look for. 99%, that's the column to look for. And the appropriate row, and please use your formula sheet. And then, clearly here, 2.5 percentage points. 2.5, 2.5, and the remaining 95, and 5 percentage points, 5, and 90. So that will allow you to get the correct confidence coefficient. Now, appreciate that as I reduce the level of confidence, I'm increasing how much probability is in this tail area. And as this is getting bigger, then the corresponding t or z value we get is going to become smaller. And hence, thinking about trade-offs and how things affect things, as this value gets smaller, other things equal, the margin of error gets smaller, and the width of the interval gets shorter. Which is exactly as we saw with the age example at the start. We went from 100% with a width of 15 down to 95% with a width of 4, I think, at the time, 33 to 37. So we're going to appreciate the trade-offs involved. Reporting an interval, precision of values. 4 decimal places is good practice for statistics 1. Doesn't matter whether it's a confidence interval, a test statistic value, a probability, or anything else. 4 decimal places, that's a good rule of thumb to stick to. So, a little example there of a confidence interval of a mean. Again, using the formula sheet is fairly straightforward, but appreciate how these different terms affect the width of the confidence interval. We set S/sigma, we have no control over, but will have an impact. We choose the level of confidence, so we choose ultimately the t or z value, so this is under our control, as is the sample size n. But all will have an impact on that confidence interval. Now I am conscious of time, you are going to get all of these slides. Just briefly I'm going to highlight the things to look for when you review these yourselves. So a simple one to begin with, looking at a mean. Now moving on to an example, political science, really opinion polls. Labour is a political party in the UK, it's a bit like the Democrats in the US, say. So here, a sample of voters, you have a sample size, a certain number of them said they would vote for a particular candidate or particular party. And you're given a particular level of confidence to use. So a very routine one, work out your sample proportion, got your sample size. Straight from your formula sheet is your formula. It's a Z value, so still table 10, bottom row, 95% confidence, the 2.5 column. That will give you your 1.96 and plug in the various values, and out comes your interval. So a simple one there on a proportion. Not long. And again. That's problematic. Okay, I seem to have disappeared. But I can remember what was in there. So you have a couple of examples of a single mean and a single proportion, different sample sizes, different levels of confidence, etc. With regards to interpretation, because we haven't mentioned anything about that yet, perhaps take the examples on the board. I am 95% confident that the true proportion, in this case, because that's what's being estimated, is between this value and this value. It is wrong to say there is a 95% probability that this value is between here and here. Why? Well, let me perhaps sketch that out for you. I think we can remove this. So remember, in that US presidential election, there were many opinion polls conducted. No doubt thousands were done over many months. And true, as time progressed, the popularity of the candidates changed. So I should really compare to different opinion polls taken at different time points, because there would inevitably be some change in that time. But let's imagine on a fixed point in time, there is whatever the population is, those who will vote, those who intend to vote, etc. But let's suppose we take that sample of voters. We do a calculation and we get, let's say, the 42% to 48%. So whatever Clinton's support, or indeed Trump's support was between 0% and 100%. Okay. So let's now perhaps sketch out this confidence interval, 42 to 48%. I'm not saying this is necessarily to scale, I'm making it slightly larger so you can see it, but let's imagine this ran from 42 to 48%. This is a confidence interval based on that sample. Interpretation. 95% confident, the support is between here and here. Clearly, there are other samples which could have been selected. Just as we looked at the heights of like 10 people to begin with. Didn't have to be you 10, it could have been another 10 further at the back of the room, say. If you have done sampling design, convenience sampling. That was convenience sampling. It would not be easy for those in the back row to have to climb over everyone else to participate in that fun game earlier. Clearly, for convenience, you were right here, right now. Made sense for it to be you. Arguably, you didn't volunteer. I volunteered you, but you had a nice time. Yeah, that's fine. You'll remember that, right? Yeah. So a different sample, no doubt, will lead to different observations. A different 10 people in the room may have had a different set of heights, slightly different sample distribution. And inevitably, this is likely, this other sample might give me a different confidence interval. Let's say 41% to 47%, say. Let me sketch this one on the same scale. 41 to, let's say, 47, covering a different range of values. The width still 6 percentage points, but now centered at a different location. And another random sample might give me yet another set of values, let's say maybe between here and here. And let's consider taking lots and lots and lots and lots and lots and lots and lots of different samples. All of the same size, all taken at the same time, all working out with 95% confidence. Inevitably, the confidence intervals which are generated will be slightly different from one sample to another. Occasionally we might get still, again, 42 to 48%. That could happen, but is unlikely to happen every single time. So there would indeed be some variation in these confidence intervals. Let's just perhaps do one more. Like this. So each line there represents a confidence interval from a random sample. Let's suppose the true level of support of this candidate was at this point here. That's the true proportion pi. You can see if I drew a line through there, all of those intervals happen to include that true value. This one here didn't. So now we can perhaps give some more visual meaning to, let's say, what we mean by 95% confidence. This is saying about 95% of the time, we would get a confidence interval, which, and we'll use the correct terminology, we could say covers or spans the true parameter value. And roughly 5% of the time, we don't. That means if I did 100 samples, typically 95 of them would have given me intervals which included the truth, and 5 out of the 100 wouldn't. Had we done 99% confidence intervals each time, remember, as I go 95 to 99, the width of these things becomes a bit wider. Okay? So all of these will become a little bit wider if they then became 99. Okay? And so now, at 99% of the time, they would cover the truth. Now, if we took lots of samples, it should be pretty clear when we get a sort of rogue one like these. But as we saw in one of those two early example questions, typically we only observe one sample. And we cannot know whether it's one of these intervals or one of these. Clearly more likely to be one of these, but we can't be certain of it. So interpretation-wise, we indeed are 95, 98, 99% confident that our interval, and those are the key words to use, covers or spans the true mean, the true proportion, whatever else you are estimating. Now, perhaps one final thing to say on the confidence intervals. Thus far, we've looked at estimating either a single mean or a single proportion. Again, you've got the formulae on the formula sheet. We did say, though, that so what we've done so far is to say there is a population which has maybe a mean of interest or maybe a proportion of interest whose value is unknown. And we take a sample from that. Okay, so that's one population, one sample. Clearly though, there may be situations where we have two populations from which we take two different samples. And so now we have a mean, mu1, and let's say a mean, mu2. Two distinct groups, e.g. Male students and female students, say. Interesting food for thought question. Gender is a variable, right? You are either male or female, correct? Yeah. Little quirky thing here to consider. Gender. My passport says M for male. Okay. Most people will classify themselves as being male or female. Okay. I say most, not all, of course. However, for the sake of simplicity, and other things equal, we prefer simplicity over complexity. Okay, other things equal. So for the sake of simplicity, it's easier to consider gender as binary, as being male and female, and thinking of these as being mutually exclusive and collectively exhaustive. I.e., you are either male or female. Can you be male and female? Well, strictly speaking, arguably you could be. And in the real world, if we are concerned about reality, arguably we should perhaps have 3 gender classifications, which is perhaps representative of reality. However, once we start to include that in our statistical modelling, it makes things a little bit more difficult. Easier to compare 2 groups than to consider comparisons across 3 groups. So let's just continue with height, and let's just consider, let's say, male and female. And there's an average height of men and an average height of women. And we may be interested in both of those values unknown. So when I have two groups, two populations, we may want to do a comparison between them. I don't care what this value is, nor do I care what this value is, but I am interested in the difference between them. Okay. Of course, if this value is unknown, and this value is unknown, then the difference between two unknowns is still unknown, of course. But there's one very special case that might interest us, would be if the difference was 0. Of course, if the difference between two values is 0, then that does mean those two values are the same. So let's go back to height. Now, it was interesting, in fact, of the I think we had about 6 females in that sample. If I remember rightly, 3 were to my right and 3 were to my left. It's actually a little bit, I didn't expect that. Why? Who thinks they are the tallest person in the room? Who thinks they're pretty tall? Stand up right now if you think you're pretty tall. Stand up right now. If, I'm not saying the tallest, but you think you consider yourselves tall. Whoa! Okay. So, let's look at now at the proportion of males v females standing up. Female, male, male, male. I got the genders right? Yay! So, take a look at it. And just very briefly, stand up if you consider yourself, may need to jump a bit here, if you consider yourselves actually quite short. That too is quite surprising, because usually, men are on average taller than women. Remember, on average, these are looking at averages, they're looking at means. So in fact, and thank you, in fact, if I took a sample, random sample of men, random sample of women, and measured their heights, I would estimate mu1 with x1 bar. Then, of course, be a sample size n1, there'd be a sample variance s1 squared. I'd estimate this group, I'd have a sample mean, x2 bar, a sample size n2, and a sample variance s2 squared. I'll make a look at, again, you've got the formula on the sheet, calculating the confidence interval for the difference between means. Now, when you are looking at the difference between either two means or two proportions, e.g. the difference between Clinton and Trump's polling numbers, then again you can use the formula sheet, type the numbers into your calculator, and out comes an interval. But the interpretation matters a great deal with these intervals for differences in means and proportions. That's my final point on the confidence intervals. A difference between these. Let's suppose, I'm just making some numbers up. Well, let's imagine for height, say, in centimeters, the difference between the means was estimated to be between these two values. That means we are 95% confident that the true difference is some value between this and this. It is a range of plausible values for this. Now this one happens to include 0. And remember, 0 was a very special case. That meant if the difference between two means is 0, then they are the same value. If the endpoints are both positive, then this will exclude 0. Just as the other way around, minus 6.7 to minus 2.3. Again, excludes 0. And hence would be indicative of a significant difference in means or proportions for proportions. Perhaps just final consideration on that. Remember, we said a normal distribution, quite good to characterize height. Well, I'm going to consider now two normal distributions. Men versus women. Now, whether or not that seems to be borne out with people in this room, but what I know about humanity generally, men do tend to be taller than women, on average. Yes, we can have tall women, yes, we can have short men, but on average, men tend to be taller than women. So, not only though are their means different, but I would argue the variances are different too. you tend to see greater variation in the height of men than you do for women. So if I was to sketch out briefly these distributions. So here is a normal distribution, let's say for men, centred, mu m, mean for men, with a fairly large variation. In contrast for women, I'm exaggerating it slightly, just for effect, but maybe something like this, whereby it's centred at a slightly lower value, because on average, men are taller than women, but the variation in the heights of women tends to be a bit less than that for men. So two normal distributions, x1, x2, or xm and xf, heights of men and women, normally distributed, but potentially with different means and different variances as well. Okay. So the confidence interval questions in the exam are in fact pretty straightforward once you know what to look for. So again, I will get those slides circulated, but within them you will find a few examples for a single mean, a single proportion, difference in means, difference in proportions. A little bit on the interpretation of those results. In particular, when looking at differences, is 0 included or not? But feel free, as and when you get those, to redo those questions by changing some numbers. Change the level of confidence, say, and see how this impacts the width of the confidence interval. Change the sample size if you want, and just experiment and see how all of these things change. There's also one or two simple examples in there about sample size determination. We'd already had said, as we vary n, that will affect the margin of error. Other things equal, bigger sample size, smaller margin of error, which is good. But more observations is more money, more time to collect. So there's always a trade-off. So what we might do is to say, and this is why, that's my final point of the confidence intervals. Why do opinion polls have 1,000 as the margin of, as the sample size? And there is a reason. Because in political science, it's accepted that 3 percentage points is an acceptable margin of error. Now this is a subjective decision, but collectively, politicians are pretty happy with that sort of margin of error. And polling figures tend to be around about between sort of 30, 40, 50% for most serious candidates or parties, say. And if you go back to the sample size determination figures, and please try and calculate this, you will find that for intervals with margins of errors of 3 percentage points, with proportions of about 40-50%, leads to at least 1,000 observations to achieve that. So it is no coincidence opinion polls are typically of this size. Now, clearly, have this figure changed, then this will have an impact on the minimum sample size. Again, I'll let you perhaps play around with those calculations, but just perhaps predict the direction of the change. If I wanted to go from a 3 percentage point margin of error to a 2 percentage point margin of error, would the minimum n required go up or down? Up, because you're thinking about your costs and benefits. That is a benefit. Okay? A smaller margin of error. That's good, but there's always a cost. The cost must be more data to get. If I tolerated a larger margin of error, that's bad. It's a cost. There must be a benefit, and that would be a smaller sample size. Play around with the formulae, and then it's a value judgment about whether or not the benefit justifies the cost. And that is a subjective decision, and there's no right or wrong answer on that. So that's a few words that I'd like to have said really on interval estimation. Don't stop, that was nice. of time. I was asked to say a few words about general quantitative issues on EMFSS. I'm happy to do so if you're okay for time.
Go ahead.
Is that okay?
I think all of us
Okay, because I know this is to be a student presentation as well. I'm hoping we can fit everything in. I'm happy to be a bit flexible tonight. Okay, I have caffeine in my system. We will continue. Now, hopefully we have some of these slides. Quantitative rationale. Oh, thank you.
I think I'll call for that.
Okay. What was it? I'll call this.
This is good.
It has. EMFSS. Oh, is that a question at the back? Yes.
I have a question about selection bias.
Yes, selection bias, yes.
So the thing is, the board's got it wrong for like two selection biases. The first would be exclusion bias, as you said, not including people who had not voted for like quite some time. Isn't like there's some selection bias of selecting from a particular area, like cities and urban population? The USC and NHS poll got it like pretty much right. They predicted a Trump win, and they were having him placed at a higher rate of like 3% percentage points. So that was basically because they included like rural areas and people who didn't have like cell phones and emails and who couldn't respond over.
Absolutely. Actually, if I may, related to that, because Brexit, I'm sure it's something you've been hearing about. Very similar situation with regards to predictions, opinion polls, and the outcome. So the opinion polls were predicting that the UK would remain in the European Union, just as the polls were predicting Clinton would win the presidency. Both cases got it wrong, and so arguably this has been a damning year for the polling sector. The polling companies are now trying to justify their existence. Why should they be commissioned to do these polls if they always get it wrong? You just mentioned there about like emails and phones and things. Interesting fact. In Brexit, depending on the contact method, and in Stats 1 sampling design, there's a section on are surveys done by post, by phone, are they done electronically, are they done face-to-face? Well, I'll give you a true story on this. In the Brexit referendum, the polls conducted by phone tended to give Remain a lead in the Brexit referendum. However, the surveys conducted online consistently gave Leave a majority in that referendum result. So, depending on the choice of contact method, you actually got very different survey results. When in fact, the online surveys were far more accurate, and they did predict a Brexit outcome than the traditional telephone surveys. So the big question is why? And this indeed has been investigated. And thinking about factors which influence things. So when you look at regression, you've got like a dependent variable y and an independent variable x. Well, arguably there are many things affecting the people's choice in the Brexit referendum. However, it was quite clear from the analysis of the results that educational level had an impact on which way you voted. Most graduates, or more educated voters, tended to vote Remain. That did not mean every graduate voted Remain. Some, highly educated people with PhDs, professors, etc., may well have voted Leave, but on average, they voted Remain. In contrast, those with lower levels of educational attainment tended to vote to leave the European Union. And in fact, thank you very much, it's transpired that online surveys are better at achieving representative samples based on educational attainment. Why, I still don't really know, but it does seem to be that if you want to reach a sample which is representative based on education, then in fact your choice of contact method matters a great deal. And indeed that may borne out in the US presidential election as well, maybe not on educational level, but the choice of contact method might reach people based on different characteristics. Now, so therefore, does that mean the contact method matters? Well, it depends. If I'm looking at height, say, I don't think necessarily why shorter or taller people are more likely to respond to an online survey or a telephone survey. So it's a question of whether factors which may affect some outcome, are these things which are likely to differ by contact method. So it depends. But I agree with your point. Those more rural areas tended to be more sort of Trump strongholds. There was still the issue, though, of many of those people tended not to have voted in previous elections. So the polling companies basically ignored them. They knew they existed. They knew they had the right to vote, but they made an assumption. They assumed because if they hadn't voted in the last 5, 6, 7 elections, why would they suddenly vote now? It was interesting. When the exit polls of the presidential election came out, Hillary Clinton was the most unpopular presidential candidate in history. Or Donald Trump, who was even more unpopular than Hillary Clinton. You had the two most unpopular presidential candidates of all time standing. Okay. But interesting. They asked in these various exit polls various questions. Do you consider Clinton or Trump honest, trustworthy, blah, blah, blah. And they varied a little bit on these figures. But there was one extraordinary result that I really caught my attention. They asked, which candidate to you represents the potential for change? Not necessarily good change or bad change necessarily, but change. And Trump was leading by a mile. About 82% of polls I saw, 82% of respondents said Trump would represent change. Things would change if Trump became president. If it was Clinton, only about 20% said there would be change. She was seen as the status quo candidate. So again, I think there are some clear parallels between Brexit and the US presidential election. The so-called disenfranchised, people whose personal circumstances have not changed much. If your income, your household income, has stagnated for many, many years, then if you continue with the status quo, and on a relative basis to the top in society, you've seen declining living standards. Well, if you vote for the status quo, why would things for you personally ever change? Whereas if you try something very different, doesn't mean things will be better for you. They could be worse for you. But arguably, you do need to take a risk if you ever want the chance of something good to happen. When people engage in higher education, globally, there will be graduates out there who don't have jobs. Okay? There is unemployment in the graduate sector. However, and so it's a bit of a risk undertaking a higher education if you don't get a job at the end of it. However, it's all about quantifying risk and managing risk. Yes, there is unemployment among graduates, but there's even higher unemployment among non-graduates. But so inevitably, if you want to have a big salary in life, if that's your main motivator, let's say it's financial, then clearly it's a necessary condition to pursue education. Not every graduate will become a multi-millionaire or a billionaire, say, but by pursuing education, you are more likely to achieve that. So the disenfranchised, I sort of said here, that was sort of the general voting, regularly voting people versus all people. I'm not quite sure what the difference in size of these two bits are, but these sort of disenfranchised ones, most elections, the candidates are quite similar to these people, and they don't see much of a difference between one or the other. So frankly, they think, doesn't matter who I vote for, my life is not really going to change, so I won't bother voting. But now, with Donald Trump, you have clearly a bit of an outlier presidential candidate. Whether you agree with his policies or not, the point is he is indeed an outlier. And it indeed will be interesting to see how the next 4 years progress. So these people are now thinking, vote Clinton, nothing will change, so why vote? But if I vote for Trump, perhaps something will change. Brexit. I would argue being a member of the European Union is good for the aggregate UK economy. However, if you are an individual whose household income has stagnated for year after year after year, maybe even gone down a bit after the financial crisis, perhaps being in the EU is good for the aggregate UK economy. But if you as an individual are not feeling those benefits from being in the EU, then you're not that bothered whether you stay in it or not. And you think, if I vote Remain, it's voting for the status quo. If we've been in the EU, I've not realised the benefits. So why don't I take a risk, take a gamble, let's vote to come out. Things will be different. Not necessarily good different, it might be bad different. But at least there's a chance, that's perhaps arguably how you could rationalise it, that maybe there's a chance things might be better for them. And maybe it will. There's huge uncertainties about what Brexit will mean. Theresa May was out here a few weeks ago, I think, trying to get a trade deal with India. Help us, please. And I think she's jetting around the world trying to get various trade deals. And maybe long term, perhaps Brexit will be a great thing for the UK economy, but no one knows. But you could perhaps rationalise things that way. You've got to take a risk. If you don't take a risk, why would things ever change if you just do what you normally do? Okay, well, just a few minutes. I'm very keen to hear the student presentation, a bit on the quantitative rationale. So what do? I'm not making necessarily just statistics. I'm thinking all quantitative stuff you do as in your studies. This is slightly UK-centric, but I think would apply pretty much around the world. Perhaps you might be able to read the headline: "Poor numeracy blights the economy and ruins lives." It was a UK study saying how poor numeracy among the population, these are not graduates necessarily, the UK population as a whole, is blighting Britain's economic performance, ruining our lives. This charity said millions of people. Now, the UK population is about 60 million, so millions in the UK is a large proportion of that population. Millions of people struggle to understand a payslip or a train timetable or pay a household bill. Now, I found this astonishing when I read that. I would not consider payslips, as when you are in employment, having a payslip, reporting what you're earning, you'd think that's something everyone would have an interest in understanding. And we're not looking at one or two not understanding this, but millions. And arguing. They say here, poor numeracy is seen as a badge of honour. People are quite happy to admit to their friends that they're bad at maths. They can't add up. It's not seen as socially unacceptable. This is in stark contrast to if someone was illiterate. If you cannot read or write, that's perhaps more embarrassing than not being any good at maths. So it's more of a cultural mindset. If people think it's okay not to be able to add up, then they're not ashamed, perhaps having poor numeracy skills. And indeed, the report goes on to look at having bad numeracy skills leads to, on average, more likely to be unemployed, more likely to go to prison, more likely to die at a younger age. Even life expectancy can be linked to numeracy skills. So I'm hoping to live to be 200. Can't add, won't add. So there seems to be some people in the UK may read that and not think there's any mathematical problem with those particular statements. Actually, if I may, can I ask you a maths question? I know you perhaps weren't prepared for me to ask you things, but if I may, I want to ask you all a maths question. Is that okay? Now, I am nice. You can confer with your neighbour. There is a department store and there's a sale. The initial price was £100. We'll do it in sterling. £100. There's a sale on at the store. There is a 50% discount. Good, get it right in there. So £100. 50% discount. What I want to know is, what is the new price of the jacket? Take your time. Whoa, very good. Now, I'm hoping you did not think that was terribly difficult. Okay. Now, I assume you are familiar with, if I say subprime mortgages in the US, or one of those things, okay. There are people called ninja borrowers. Did anyone hear that phrase, ninja borrowers? Oh, you did, okay. What did ninja stand for?
No income, no.
Good. No income, no job or asset. The ninja borrowers. These were not people going, whoa! Not those sorts of ninjas. Ninja borrowers. So in the lead up to the financial crisis, I don't know, I'm familiar whether this would be shown here. The Big Short, is that, okay. That's a great film, very well written, some lovely lines in that, nicely conveys sort of the financial crisis. They're trying to demonstrate the typical ninja borrowers. These were people in the run-up to the financial crisis. No income, no jobs, no assets. So you may wonder, how on earth did such a person get a mortgage? Okay, if they have no income, no jobs, and no assets. Yet these people, in the go-go years, could very easily obtain a mortgage in the US. Now, after the financial crisis, some researchers wanted to determine the financial literacy of ninja borrowers, among others. Okay. Now, you did very well with that £50, and that is indeed the correct answer. They took a sample of ninja borrowers. They gave them 10 maths questions, all of that level of difficulty, or if I may say, simplicity. And to these people, they had access to computers, calculators, they could discuss amongst themselves, I believe. And out of 10, and all these questions were of that level of simplicity. And they could have as long as they liked to work out the answer. They were averaging about 2 out of 10. Now, if you imagine, people struggle to make those sorts of calculations. How on earth can you understand the complexities of a mortgage? A mortgage with variable interest rates. Oh, what are those things? A teaser rate which will then change, and maybe that interest rate is tied to the central bank interest rate, etc., etc., etc. If millions of people cannot understand a household bill, or a payslip, or a train timetable, how on earth can people fully understand a mortgage? So, many of these ninja borrowers, they were getting, signing up to mortgages that they didn't really fully understand. What they were sold was basically, sign here, you get these keys to this nice big house. Next month and the month after, you've only got to pay me this small amount of money. Don't worry about after that. So clearly, people sign on this dotted line, they like to get the keys to that nice big house. So, had the global population been far more numerate, and when I say be numerate, that does not mean knowing how to work out angles of a triangle, basic geometry stuff you do at school, but basic life skills like interest rates, the time value of money, simple percentages. Okay? These are things which arguably everyone really needs to know. Now clearly at degree level we want to go a little bit beyond that, but this is why at the core of your degree programs are many quantitative courses. I say like be ahead of the competition. Once you graduate from here, you'll be no doubt looking to pursue some degree somewhere doing something, but I think having a quantitative background will make you a very valuable asset to any employer. So I implore you to study as much quantitative work as you can. Indeed, you are welcome to read beyond what you find in subject guides. There is nothing stopping you buying a book online and reading it for self-study. Not at the expense of your core studies. Of course, you've got to do well in your exams. But feel free to read up more on data analysis, that kind of things. It will serve you very well going into the future. I remember roughly what was in there. So, with the EMFSS, what do we do? Actually, I'd love to show you this it's not displaying here, but I'd love to give this as an example of what really the quant courses in EMF care about, what's out there, known as the real world. We've already said today, the real world is a little bit complicated. Gender, how many genders are there? Well, it's a bit complicated. The real world is complex. Do we like complexity? Other things equal no, we value simplicity. So what we try to do is to build models of the real world. A model, be it in economics, mathematics, statistics, utility functions, you do Lagrangians, things like that. These models are simplifying the real world. A good model will retain the most important features of reality and ignore some less important details. So indeed, that London Underground map is a lie. There's a line called the circle line. Why do you think it's called the circle line? You think it goes around in a circle. Well, arguably it does sort of come back on itself, but it's not a perfect circle. The tunnel under the ground is not a circle. That Victoria line on the map would have been shown as some straight lines, maybe bending a little bit here and there. When you went on the line, did you feel you were going in a straight line, or were you trying to, go like that? Yeah. So the map is a lie. Okay? The map does not represent how the tunnels move under the ground. the map tells you nothing about the depth of the tunnels under the ground. You no doubt went down an escalator or down a lift to get from the street level down to the platform level. That information is missing from the London Underground map. Is this a problem though? No. If your objective is to get from point A to point B, whichever stations it was on the Victoria line, you were able to use that map to make that journey. So I always hold up the London Underground map as a great example of what a good model should be, i.e. not reality, because reality is too complex. I don't need to know the depth of each tunnel, each line on the London Underground. I do not need to know exactly how the tunnel moves and curves around under the streets. I just need to know the order of stations on a line. I need to know where lines intersect. That's really all I need to know, and I can get from point A to point B. So as and when you pursue more courses in economics, management, finance, whatever it may be, maths and stats, one hopes, you'll see lots and lots of models. And this is our attempt to model the real world. Do we get it right all of the time? No. People can make mistakes. If I may, anyone interested in moving into finance longer term? Okay. Finance. We mentioned the normal distribution, we mentioned the t-distribution. Okay. There's the normal distribution. Let's say the standard normal distribution. Often, models, financial models, may assume standard normal distribution for simplicity. That's one of the first distributions you study in any great depth. You did the normal before you did the t, the chi-squared, say. We know a lot about the normal distribution. It's a nice distribution to use. However, if we are interested in modelling the returns of stocks, say, then many models assume normality. Sadly, the real world is not entirely normal as far as stock returns are concerned. Anyone heard of the book The Black Swan? Okay, what is a black swan? It's an extreme event. Something like a Brexit result, something like a Trump election win, okay? Something like a financial crisis caused by ninjas. These things happen. Do they happen all of the time? No. However, a t-distribution relative to the standard normal has these so-called fat tail distribution. Peaks lower, but to retain that total area of 1, those tail areas become a bit larger. So little use of the t-distribution. Various studies have shown that stock returns, so if you want to predict stock returns or whatever in the future, things like a t-distribution with about 3, maybe 4 degrees of freedom, so far fatter tailed distributions than the standard normal, in fact, more closely approximate stock returns than the standard normal. Why? Well, I want you thinking of these as being black swans, extreme events. So we had a very short, very tall person in that sample earlier. Arguably, we could have had even more extreme outliers there. But just think about 2016. It's been a year of black swans, arguably. Brexit, Trump, Leicester City. I'm not a football fan, well, except you are here. But Leicester City, I believe, there were 5,000 to 1 outsiders at the start of the season. They won. And indeed it seems, there seems to be a bit of a cycle, about once in every 20 years, one of the non-top teams tends to win the Premier League. So we're about sort of time due for that. But I think this year, 2016, will go down in the history books as being perhaps a year of the main black swans. I.e., these extreme events may be good, may be bad, but they happen a little bit more frequently than a standard normal distribution would predict. So if you have various financial derivative models produced by quants in banks and hedge funds, say, if they're making assumptions of normality, yes, we do make assumptions to make our lives simplistic, but as and when you pursue more models in EMFSS, there will be assumptions attached to them, but you need to pay great attention about the validity of those assumptions. If you build a model, as beautiful as it may be, if it's based on flawed assumptions, it could lead to some pretty bad outcomes. Indeed, these ninja borrowers were being able to borrow all of this money. Why? Because there was an implicit assumption that house prices in the US would only ever go up. So you give someone a house, give them a loan, and they default, so what? The bank repossesses or forecloses the house, and so what? They can sell it, it's gone up in value, the bank gets the money back. So the bank's happy. So that was an assumption. And for many years, house prices went up and up and up. All good. But then, house prices started going down. The model said, oh no, we didn't predict this. So, quantitative work in EMFSS. We are trying to understand the real world. LSE's motto in Latin, rerum cognoscere causas, translation, to understand the causes of things. That's what LSE is trained to do. And the UOL international programs were designed by the LSE, and indeed we are trying to make you understand the causes of things. And clearly, yes, well, we like qualitative things, the observations about how I look to say how old I am. Qualitative insights are useful. I'm not saying they're not, but so too are the quantitative sides as well. And arguably, we need a blending of the two to really be optimal. So really, one does need a good set of quantitative skills, and that's what the EMFSS is trying to instill in you through your maths, statistics, etc. So I'm not saying necessarily that as and when you graduate and do whatever jobs you do, you may never do another Lagrangian problem again like you do in Maths 1. You may never design an actual quota sample for real in life, or work out a confidence interval for those police officer reaction time of learning these things. I'm sure for most graduates, maybe 90% of what they learn at university they don't actually use in the real world. That's not to say the university education is a waste of time. It's all about working on what's up here and developing your brain, developing your problem-solving skills, such that whatever careers you go on and do, and assuming you're going to go on to great things, then clearly you're going to be exposed to a range of challenges and problems for which there is no off-the-shelf solution, and you've got to design some bespoke solution to a problem. And the whole point of the EMFSS is to train your brains to be able to react to whatever life throws at you in your careers and your lives more generally. So, I implore you to take your quantitative courses extremely seriously. They are of great value to you, not just to help you get a good degree, but these skills will serve you in very good stead in life going forward. I am conscious of time. I do want to hear the student presentation. I can perhaps take one or two quick questions, otherwise I can shut up.
Any questions? I think everything is clear tonight.
Is it? Is it good? I hope so. I hope so. What is the answer to all of life's questions?
It depends.
That does not mean in May, in your UOL exam, in your answer booklet. You're right. It depends, it depends, it depends, it depends. James says it depends. It depends may very well be the answer, but there needs to be a justification for that answer. Show your method, explain your results. Whether it's stats, maths, economics, or anything else, please make sure you do that. Okay, well, thank you very much.